So section 5.1 here. The title of this section is Angles and Radian Measure. And I'm basically just going to throw a whole bunch of definitions at you today, and we'll talk about those definitions. Okay. And a lot of these definitions are kind of like dumb definitions, like, why are we defining this? I already know what this is, right? I know conceptually what it is. I don't need to know a formal definition of it, but still, it's a math class, so I have to do it, right? So our first subheading here is we're going to be talking about, well, what even is an angle, right? So let's have a little note here, okay? So as a note here, I like to say that an angle is a measure of rotation. Okay, a measure of rotation. Okay. Right, and some textbooks will define it that way as well. All right, this textbook, though, doesn't really do that. It defines it as a, well, I'll show you in just a second anyway. Okay, so now let's formally define this thing. Okay. DEFN is my abbreviation for definition. Okay, so anytime I'm defining something really important, I'll probably have this DEFN next to it. Okay, and then I'll underline the word that I'm defining. Okay, so the first definition here is for a ray, right? A ray it's a half line, basically. So it's a part of a line that has only one endpoint. Oh, this is the worst way to spell only ever. Let's see. Let's try that. Only. Oh, that's just beautiful. Okay. Only one endpoint. Okay. So like I said, I'm trying to work on my my handwriting here. Okay. So array is a part of a line that has only one endpoint. So here's a picture of that. There's an endpoint, and then here's just a direction that the ray goes off in, right? Yeah, so just half of a line, basically, right? The line extends off into infinity in both directions, right? Okay. Okay. An angle is formed by two rays that have a common endpoint. That have I think I just need to slow it down. That's probably what I need to do. A common endpoint. There we go. An angle is formed by two rays that have a common endpoint, right? And so what does that look like? Well, we have a common endpoint. So we're going to have two rays coming off of this thing. Let's say one of my rays is going this way, right? A blue ray, right? And then another ray is going off this way, a red ray, okay? And then an angle is formed by these two rays. But really, there's two different angles we could be talking about there, right? We could be talking about this angle between these two rays here, or we could be talking about this angle right over here, right? Okay, so we have to say, like, basically which one of these angles we're talking about. Okay. So for instance, let's say we're talking about this one. Okay. I'm going to define a few more things that has to do with this. Okay. So one ray is called the initial side. Let me write that a little bit neater here. The initial side. Okay. And the other is called the terminal side, okay? So initial side just means starting place. Terminal side just means ending place, right? So really we're rotating from this blue to this red over here, let's say, right? So you see I have a direction of rotation there, right? So now we know we're starting at the blue side and we're rotating up to the red side, right? Okay, so we'll say that this blue side then is the initial side, since that's where we started. And then after rotating, we get to the terminal side. Okay, fair enough. All right, now this point over here, this common endpoint of these two rays, right? That's called the vertex. Vertex. Okay. So I'm going to label this part right over here as the vertex. Okay. And so I'll refer to the initial side and the terminal side and the vertex quite often. Okay. So I just want to throw those definitions out there in case we maybe forgot them or never seen them before, right? This is probably a good question to ask, because this has happened to me before. Is there anybody in here who has not had like high school geometry? Okay, so a lot of these words we already know. We've studied angles, right? We've studied triangles, we've studied circles, and we've studied like rectangles and so on. Okay, so that's good. I have had a student who has never had like a high school geometry course, so like, I just wanted to be sure, like, that we're not going too fast, basically. Okay, so those are some important definitions, right? Now, let's do a note. We often use lowercase Greek letters. Oh, sorry, let me underline this. We often use lowercase Greek letters for angles, right? So, for instance, here we might use alpha, right? So that's ALPHA. That's pronounced alpha, right? Or we might use beta. So that's BETA, beta, right? Or gamma sometimes, yeah. GAMMA. I don't really use that one. Probably the most common one I use is theta, right? So this is THETA. Okay, so I'll use alpha and beta and theta a lot, probably. Sometimes I'll use uppercase English letters or Arabic letters, right? So sometimes I will use uppercase English letters. I'll just say English letters, even though it's the Arabic alphabet. Okay, so like capital A, capital B, and so on, right? Or sometimes I'll use like U and V sometimes. Okay. Okay. So good. Now, next subheading here is on standard position. Okay. Which is super important. Okay. So I'm going to scroll it up to right here. Is that all right? Okay, so let's do some definitions here. Let's see how neat I can write this. All right, so definition. An angle is in standard position. Standard position. Okay. If there are two conditions that need to be satisfied here. Okay. Its vertex is at the origin of a rectangular coordinate system. And what do they mean by rectangular coordinate system? Well, they just mean the XY plane. Yeah, I don't know why they didn't just say that, right? Yeah, so the XY plane, right? And what do they mean by origin? Well, the origin is just the point 0, 0, right? It's where your two axes cross. That's the origin, okay? Right, so the vertex of your angle has to be there, right? At that center of the XY plane, okay? So that's one condition, okay? The other condition is that, that's all right, and its initial side, I don't care about its terminal side, but its initial side lies along the positive x-axis. Lies along the positive x-axis. Okay. Fair enough. So let's look at that then. Okay. So let's draw some axes. There's my x-axis. There's my y-axis. I'm going to do two examples, really. Okay. Okay. So, I'll go ahead and put my vertex here in black. Okay. So there's my vertex of my angle. Remember, the initial side has to be along the positive x-axis. Okay. So there we have it. That's my initial side of my angle. And I don't really care where my terminal side is. It's already in standard position as long as those two conditions have already been met. Vertex is at the origin. Initial side is on the positive x-axis, right? So here is an angle. Let's say it's this angle that rotates from the blue to the red like so, right? Call that alpha. Sure, why not? Okay, so here's an angle in standard position. So I'll say alpha is in standard position. Okay. Now I'm going to draw a different picture here. So still have the vertex at the origin. Still have the initial side on the positive x-axis, which means it's in standard position, right? Let's say the terminal side is in the same location over here, okay? But now I'm going to rotate from the initial side to the terminal side this way, okay? That's still in standard position, okay? So alpha is in standard position still, okay? But clearly they're different angles, right? Yeah, one is rotating counterclockwise, the other one's rotating clockwise, right? So canonically, which just means that traditionally, this is the way that everybody does it, basically. We say that the counterclockwise direction is the positive direction. So I'll say that alpha is a positive angle in this scenario, right? Here we're not multiplying, rotating counterclockwise, right? Here we're rotating clockwise, right? So we'll say that that's a negative angle. Alpha is a negative angle, okay? So I'll make a little note down here that says, by convention, which just means that this rule was created a long time ago. We're going to stick with it, right? It has to do with the apparent position of the sun in the sky in the northern hemisphere, basically. So by convention, the counterclockwise direction, which I'm going to abbreviate CCW, okay, is positive. And clockwise, which is CW, is negative. Okay. Could we redefine all of trigonometry to do it in the opposite way? Sure, we could, right? But you know, then nobody would agree with the results that you had because it'd all be like negative what they should be, right? Okay. So any questions on that so far? Right? Positive direction, counterclockwise, right? Negative direction is clockwise. All right. Good. So now that we've done that, how about we have a definition here? Okay. I'm going to define the quadrant. So this is an algebra definition, right? The quadrants of the Cartesian plane or rectangular coordinate system, or you know what, I'm just going to say the XY plane. Okay, just keep it short here, the XY plane. So the quadrants of the XY plane are the following. Okay, so I'm going to draw some axes here. Here's the x-axis, here's the y-axis, and we can see that the horizontal axis there and the vertical axis, they separate the xy plane into 4 parts, basically, right? So that's why they're called quadrants. This is your first quadrant right here. You know, I'm just going to put instead of a Roman numeral 1, which I hate, I'm just going to put a regular 1. There we go. That's quadrant 1 right there. Okay, and then quadrant 2, 3, and 4 follow in a counterclockwise rotation from here, right? So this would be quadrant 2, this would be quadrant 3, and this would be quadrant 4. Okay, fair enough. I'll go ahead and formally define what these are, right? So quadrant 1, right, which I'm always going to abbreviate as Q1, right? This is the set of all ordered pairs, x, y, such that x is positive and y is positive, right? Fair enough. So if you're in this quadrant and you have a positive x coordinate and a positive y coordinate, right? And similarly, we will define quadrant 2 here. ordered pairs, right? Now you're to the left of the y-axis, so then you have a negative x coordinate, but you still have a positive y coordinate, okay? You could probably fill the rest of these out, but I'll go ahead and do it anyway. Q3 is the set of all ordered pairs such that now we have x is negative, y is negative, and then quadrant 4, Q4. It's a set of all ordered pairs such that, well, now we're to the right of the y-axis again. So x is positive, but y is still negative, okay? Those curly braces, that just means we're starting a collection of objects, right? And then over here, that's right after that first curly brace, that's the type of objects that we're holding, ordered pairs. And then after the colon over here, that's a description of what x and y need to be, right? Fair enough, in order for you to be in this collection. Okay, so that's the way that we read this, right? It's the set of all ordered pairs such that x is greater than 0 and y is greater than 0. Yeah. Okay, fair enough. All right. Just in case you should see that kind of notation in, like, your homeworks or something. Okay. Okay, so then now that we have that, right, now that we have these quadrants, right, let's talk about what it means for an angle to be in a particular quadrant, right? If the terminal side of an angle, let's say call it theta, in standard position, let's say lies in a particular quadrant, lies in a particular quadrant. Then we say that theta itself lies in that quadrant. Okay. It's just harder to say the terminal side of theta lies in a particular quadrant, right? We're always looking for shortcuts, easier ways to say things. So we'll just say that theta itself lies in that quadrant, right? So theta is in quadrant 1, theta is in quadrant 2, theta is in quadrant 3, theta is in quadrant 4, right? If the terminal side is in that quadrant, then the angle is in that quadrant, right? Fair enough. Yeah. Now remember, this theta has to be in standard position to begin with. So if it's in standard position, we already know that its vertex is at the origin and that its initial side is on the positive x-axis. That's why we don't talk about the initial side, because it's always on the positive x-axis. It's just wherever the terminal side is that determines what quadrant we're in, right? Okay, fair enough. Okay, so in this example above, we have alphas in quadrant 2 in both of these, right? Yeah, so maybe I'll write that over here as well. Alpha is in, and I always abbreviate it as Q2. Here, alpha is still in Q2, right? Okay. Any questions on that? Yeah, right there. No problem. All right. Any questions on that? All right. All right, so the next subheading here, right, now that we've talked about angles in standard position, right, we can start talking about measuring angles using degrees, okay? Measuring angles using degrees. Okay. Which is probably the one that we're most comfortable with. Okay. So I'll make a little note over here. And let's call it a definition, actually. Okay, because I am actually defining something here. So, this at least goes back to Babylonian days. So apparently, the Babylonian, why can I not spell today? Babylonian and Persian calendars had years that were 360 days. right? 360 days. And so they organize their entire number system around that fact, basically, right? Instead of breaking things into hundreds, they broke things up into 60s. They had a base 60 numerical system and so on. And so then 660s made like one full circle. And they thought that, oh, okay, this is great because it has so many divisors and everything like that, right? And so now they pass that on to the ancient Greeks, who pass it on to the Romans, and so that's why we use 360 degrees, basically, right? And so having that, so then the time it takes for one full revolution, right, which is what a year is 360 days, right? And I'll just say is broken up into 360 equal parts. How about that? Into 360 equal parts. Which we call degrees. So a degree is just 1/360th of a full rotation, basically. Yeah, that's all a degree is. Okay. So now that we have that, right? Oh, yes. And we write 1 degree, right? So that's how we do the degree symbol, right? Okay, so now that we have that 360 degrees is one full revolution, right? Now we can start making some special angles here. So an acute angle is an angle measuring less than 90 degrees. Right? A right angle measures exactly 90 degrees, right? An obtuse angle is greater than 90 degrees, but less than 180 degrees. Very important there, right? And then a straight angle is exactly 180 degrees. Okay. And I guess for an acute angle over here, I should say it's a positive angle. A positive angle, right? Can't be 0 degrees. Has to be at least positive, right? Okay. So a positive angle measuring less than 90 degrees. Yeah. Fair enough. Okay. So any questions on that? Right. And I think that these again are all definitions that we've seen before anyway, right? Yeah. We've seen before. Okay. Let's see. We get out of here at 12:15. Right. Okay. Okay, so now that we have that, right, let's talk about measuring angles using radians. Okay. Okay. So before we can define what a radian is, right, we need to define a central angle. So let's suppose we have a circle. Okay. In a circle, right, a central angle. Central angle is an angle whose vertex is at the center of the circle. Okay, so that's a pretty easy definition, right? So it just has to have the vertex at the center of the circle. So let's just draw a little quick picture here. Here is approximately a circle, right? Here is the center of that circle. And then we have some initial side right? Let's say maybe it shoots off this way. Nope. Where is my colors? There you go. There you go. And then we have a terminal side. Okay. And let's say it's rotating in this direction. Why not? Right. So that's a central angle, right? I'll call it theta. Okay. So theta there is a central angle. So all it takes is that the vertex is at the center of a circle. And now you're a central angle. Okay. Now, an arc is a small connected portion of the boundary of the circle. Just the boundary, though, not the interior. Trapped between the initial side and terminal side of some central angle. Oh, let me scroll up a little bit. Sorry. Of some central angle. Okay. So then right over here, that's an arc. Right there from, let's see, kind of bolded in there. This is an arc because it's what's trapped between that central angle. Okay. Any questions on that? Now that arc, right, it has some length associated to it, right? It goes from here along the boundary of the circle up to here, right? It's kind of hard to measure that length though, right? Because it's along this curved wall basically. But I mean, if you were to take a piece of string and tie it over here and stretch it taut over here, right? Then you could like, measure the length of that string, right? Take it and now stretch it out over a ruler and then you can get the length of that, right? So the length is well defined anyway, even if it is kind of hard to measure what the length is along a curved surface like that. Okay. So having that, we'll say the length of the arc is called, give me 1 second here, is called the arc length. That's what it's commonly called anyway. Okay, arc length. All right. So now that we have that, right, I think we're ready to define what a radian is. Okay. So let's start a new definition here. 1 radian, okay, is the measure of a central angle right? So we're saying that the central angle has a measure of 1 radian, right? Under what conditions, right? Right? It's the measure of a central angle in a circle of radius r, right? Because it's a central angle, so we have to say what the radius of that circle is. Circle of radius r, such that the arc length is equal to the radius r. Okay, so I want the arc length to be equal to the radius r, right, inside this central angle. So basically, yeah, you can imagine we have a central angle, right? And we start rotating that terminal side and we say, well, what does the arc length look like? That's a lot smaller than my radius. So I'll keep on rotating. I'll keep on rotating, 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 rotating until I eventually wind up with an arc that is exactly the same length as the radius of the circle. Once that is achieved, you have officially rotated 1 radian. Okay. So you stop rotating when that arc length is the same length as the radius of the circle. Okay. That's what a radian is. That's how much rotation you need in order for your arc length to be the radius of the circle. Okay. So I'm going to draw a little picture here. Okay. Central angle, right? And so let's say that my initial side is right here, right? My terminal side is, well, before I do my terminal side, let's say that the radius of the circle is r, right? So then I need my arc length to be r. And remember, this is a curved surface, so it's kind of hard to tell like where that where you need to stop at for it to have a length of r, right? Let's say it's about right there. So this arc length right here, from here to here, that arc length is equal to r. If that happens, then we say that this rotation, right, this angle theta, we'll say theta is 1 rad. Okay, 1 radian of rotation. Okay. Fair enough. Any questions on that? Because this is probably one of the most confusing concepts we're going to cover today. Yeah. How do you know if they're equal? Yeah, I mean, like, we know that it's theoretically possible, though, right? Because it's continuous, right? Yeah, we can keep rotating until finally it does happen, right? Like, can we do it on a real circle? Yeah, we can do an approximation. We can say, we can just keep measuring the arc length and say, okay, that's almost the radius of the circle. Keep on going, keep on going. Oh, it's gone too far. Let's go back, right? So, I mean, yeah, I mean, we can achieve this in real life as well. But of course, we know that it's theoretically possible for the arc length to be the same as the radius of the circle, right? So at that theoretical place, that is a 1 radian angle. Okay, fair enough. All right, other questions on that? All right. Now, of course, we can go 2 radians if we wanted to, right? If we wanted to go 2 radians, that would mean that we rotate 1 radian first, so then that arc length is r. And then now we rotate again by another radian, and now we have 2r is that length, right? 3 radians, right? We would have 3r is the length of the arc. 4 radians, we'd have 4 times r is the length of the arc, and so on and so forth. So it gives us this kind of nice way of measuring the arc length, right? If I know the number of radians it is, then if I multiply it by r, then I get my arc length. That's easy, right? Fair enough. So that's why we like radians so much, right? Because all we need to do is just take your angle measured in radians, multiply it by r, and now you have your arc length, okay? So that's a formula. Let's say this. So the length of the arc, right, which I'm going to call S. That's a pretty standard notation for the length of an arc. We'll just call it S. I don't know why they chose S to begin with, but yeah, usually when you see S, it's the length of an arc, okay? So the length of the arc, which we're going to call S, right, is given by S is equal to R times theta, if theta is measured in radians. Right? So if theta is measured in radians, then we have that, right? Okay. Okay, so I'll write that as a little note over here. So any questions on that? All right. Any questions on that at all? Okay, so good. Now that we have that then, let's do the following. All right, this will be another note on radian measure, right? Let's suppose that I know the radius of the circle. That's pretty easy to check what the radius of a circle is. I also have an arc on the circle, let's say between 2 points on the boundary, right? And I can measure the length of that arc. And I want to know, well, what is the angle, right, that gives me that arc length, basically? Yeah. So consider an arc. An arc, try to write neatly. I always forget like halfway into it, like, so I have to go back and edit it. Consider an arc of length S on a circle of radius R. The measure of a central angle, or of the central angle, theta, that intercepts, right, the arc. And all that means is it's a central angle that forms the arc. The arc is trapped between the initial and terminal sides of that angle, right? That intercepts the arc is, so here's the formula for it. Theta is equal to S divided by R. right? Which is just the same equation as this if we divide both sides by r, right? Yeah. So arc length can be gotten from angles and radians, and your angle measure in radians can be gotten from from this formula here, where the arc length divided by the radius, right? Radians are best thought of as a conversion factor between arc length and the radius of a circle. Okay. I'm going to come back to that in some examples later, like why I'm defining it that way. It's just sort of conversion factor. It's best thought of that way. Okay, so this theta, if you take the arc length and you divide it by the radius of the circle, then you're guaranteed that this is your angle measure, and it will definitely be in radians because you're comparing the arc length to the radius of a circle, hence rads. Okay. All right, so let's do an example just so we can, use the formula, see how it works here. Okay. Yeah, we got time. A central angle, theta, in a circle of radius, let's say 12 feet. It's a big circle. Intercepts an arc of length 42 feet. What is the radian measure of theta? Right? All right. So we're just using a formula is all we're doing there. Okay. Now, fortunately, our arc length is measured in feet and our radius is measured in feet. As long as they're measured in the same distance units, then we're good. But if one of them was measured in inches and the other one was measured in feet, we'd have to convert to a common unit first. Either convert them both to inches or convert them both to feet, basically, right? They have to have the same dimension there, right? Okay. So using my formula, we know that theta is equal to S divided by R, right? S is the arc length, which is 42 feet, right? R is the radius, which is 12 feet, right? And so we have feet in the numerator, feet in the denominator, right? And so the feet cancel off, right? Yeah, so it seems like on the right-hand side, this thing is dimensionless, right? Because our units have gone away. Our feet have canceled off with our feet, right? Okay, but remember what radians are. They're a conversion factor from the arc length to the radius of a circle. So here is what we're doing. We're comparing the arc length to the radius of a circle when we're dividing S by R, right? So then the units should be in radians when we do that. Okay, so 42 over 12. When the feet cancel off, we'll be left with rads. Okay, so let's just simplify this a little bit. This is like what, 3.5? 3.5, and the units are rads, radians. Okay. So any questions on that? Arc length. Yeah. Radius of the circle. Yeah. Yeah. So I'm probably always going to use S for arc length. Sometimes I may use capital L also. Yeah. So. All right. Any questions on that at all? Okay. So good. Now we've talked about degrees, we've talked about radians, but there's of course a relationship between degrees and radians, all right, which is going to be our next subheading here. Relationship between degrees and radians. All right. So let's make a quick note here, because we talked about some things already, right? Like we know that one full revolution, REV stands for revolution, right? That's 360 degrees, right? We rotate full circle, we've gone 360 degrees, right? Okay. We also know that one full revolution is 2 pi rads. And you might say, well, why do we know that, right? It's because the circumference of a circle is 2 times pi times r, right? It's kind of how pi was defined, actually, right? As pi times the diameter is always the circumference of the circle, right? So 2 times pi times the radius is the circumference of a circle, right? Okay. But then, of course, that's just an arc length. of an arc that starts and ends at the same place. So the arc length should be theta times r. So then 2 pi r is equal to theta times r, which means theta is equal to 2 pi when we've gone one full circle. There you have it. Okay. So then 1 revolution is 2 pi rads. Okay. Fair enough. Okay, so now we know that 1 revolution is 360 degrees. 1 revolution is also 2 pi rads. So that must mean that 360 degrees is the same thing as 2 pi rads. Right? All right. So that's a nice relationship, a nice easy relationship. But we can make it even easier. We can divide both sides by 2 and it'll still be true. Right? As long as we're doing the same operation on the left-hand side as on the right-hand side. So then 180 degrees is the same thing as pi rads. Okay? Any questions on that? Okay. So now that we have that, right? Well, then if I divide both sides by 180 degrees, right? Then we have that 1 is going to be equal to pi rads divided by 180 degrees, right? So I've just divided both sides by 180 degrees. So my degrees cancel off with degrees, and I truly have a unitless thing here. It's just 1, right? Now, why am I doing that? Why am I writing 1 in this funny way? There's a math trick that we use quite a bit where we multiply some quantity by 1 because we don't want to change the value of that quantity. So we just take this quantity, we multiply it by 1. So we haven't changed the value at all, right? But we'll multiply by 1 in a funny way in order to get some cancellation. Yeah. So I'll show you in an example here. Okay. I'll show you in an example here. Let's say we have, how about 36 degrees, right? Now that's some angle, 36 degrees. I want to know, if we were to measure that same angle in radians, how many radians would it be, right? Yeah, we're measuring the exact same angle, but I want it to be in radians instead of degrees, right? So here's what I'm going to do. I'm going to take my 36 degrees. I'm going to multiply it by pi rads, and I'm going to divide it by 180 degrees, okay? Now, why can I do that? It's because pi rads over 180 degrees is really just 1. So 36 degrees times 1, right? That's the same thing as 36 degrees. I haven't changed the value at all. I'm just multiplying it by 1, right? But I'm multiplying it by 1 in a very funny way, right? Okay. Now, what is the advantage of multiplying it in such a funny way here? Well, I am multiplying by degrees, but I'm also dividing by degrees. So my degrees are going to cancel off. So the only units I have left are radians, right? So then this is the same thing as 36 times pi divided by 180 rads, right? Any questions on that? Any questions at all? All right. Now, 36 and 180 happen to both be divisible by 36. So this is really just going to be pi over 5 rads after we reduce it, right? Which, of course, MyLab Math, they want a reduced fraction, right, in terms of pi for your answer there, right? So 36 degrees is the same thing as pi over 5 radians, okay? Yeah. I'm going to show you in just a second here. Yeah. So, all right. So let me give you the general formula here, right? So this is conversion between degrees and radians. Degrees and rads. Okay. So if theta is measured in degrees, then take your theta, multiply it by pi rads, divide it by 180 degrees, right? And then your degrees will cancel off and you'll be left with radians. So this will be the angle, the same angle, I'll say. The same angle measured in rads. Okay, fair enough. So if I want to convert from degrees into radians, I multiply by pi rads, I divide by 180 degrees. Okay. On the other hand, right, if theta is measured in rads, then I'll take my angle, I'll multiply by 180 degrees because I want to convert it to be in degrees. right? And I want to cancel off the radian, so I'll divide by pi rads, right? Is the same angle measured in degrees. Okay. All right. Any questions on that? All right, so all I'm doing is multiplying by 1 in a funny way in order to get some cancellation, right? All right, so let's try an example now. And the way that these will probably be phrased, right? And they could come in many different forms, but the way that this was phrased in the textbook here is just says convert to rads, right? And so they gave you, let's say A is 30 degrees. I might have come up with some of these. B is 90 degrees. And C is negative 135 degrees, let's say. Okay, and I want to convert each one of those into radians, okay? So let's do it, okay? We're going to use our formula, okay? So for part A here, we have 30 degrees, right, is equal to 30 degrees times 1, right? Fair enough, because all I'm doing is multiplying it by 1, right? But I'm multiplying it by 1 in a funny way, right? So if I'm going from degrees into radians, right, then I need to multiply by pi rads and divide by 180 degrees, right? And this way my degrees will cancel off, right? I'm going to write this as 30 pi over 180 to begin with here, right? You could have gone ahead and simplified it if you wanted to, but 30 over 180 is the same thing as 1/6, right? So this will be pi over 6 rads. Okay. Any questions on that? All right. So then now we'll do part B then. We have a 90-degree angle, right? So that's going to be 90 degrees times 1, right? But I'm multiplying by 1 in a funny way. Multiplying by pi rads, dividing by 180 degrees. Okay, my degrees cancel off, which is good. 90 over 180 is 1/2, right? So this will just be pi over 2 rads. Okay. Okay. Now we'll do negative 135 degrees. Am I going too fast? Yeah. All right, I'll slow it down a little bit. Yeah. And if you have any questions, just stop me in whatever I'm doing. I'm happy to answer questions. Yeah. It doesn't matter the mode. It only matters the mode when you're doing trigonometric functions and you're plugging angles in, like sine and cosine and tangent. So like it could be in any mode you want to if you're just doing this algebra, basically. Yeah. Okay, fair enough. Now, saying that, there might be a function on the calculator, maybe, that when you just give it an angle in degrees, it might be able to convert it to radians automatically, right? But I mean, it's just as easy to multiply by pi and divide by 180. So. All right, so now we have negative 135 degrees, okay? Which is the same thing as negative 135 degrees times 1, right? But I'm multiplying by 1 in a funny way. So I'm multiplying by pi rads. I'm dividing by 180 degrees, right? Now, negative 135 and 180 are both divisible by 45, okay? So 45 goes into this negative 3 times. 45 goes into this 4 times. So this is just going to be a negative 3 pi over 4 rads, okay? On the subject of simplifying this in the calculator, actually, let's see. Let me pull up my calculator here. You can see over here. This is the worst setup ever. Okay. Yeah, let's get my TI-84 Plus here. Silver edition. Okay. So on the subject of simplifying things in on the calculator here, let's do this. If I take 135 divided by 180, right? That's the fraction I'm trying to simplify, right? So just ignore the pi, basically. Let's just try to simplify this fraction, right? So 135 over 180. Obviously, if I plug this in, it's going to give me a decimal approximation, 0.75. Now, you may recognize that as 3/4, right? But the calculator will actually transform it into a fraction. If you go to math over here, this first option, this arrow sign that says frac, that means convert to fraction. So we can click on that, and it'll take your previous answer, which was 0.75, convert it to a fraction, right? And then you have that this is 3/4, right? So then multiply that by pi, you now have 3 pi over 4, right? Okay. So that's great. Yeah. Does it always work? No. Sometimes when you have like these really huge numbers, calculator doesn't know what to do with it. And what are huge numbers? Like in the tens of thousands, really, I think. Yeah, I mean, this is kind of like, I mean, it's a very powerful device, but, it's old. Yeah. So anyway, I just wanted to show you that. Okay. So you go to math, and the first option there is convert to fraction. Okay. Yeah. I don't know if I said this to this class in particular, but I do advise you to get a TI-83 or a TI-84 calculator. They're really good machines. Yeah. Okay. It's not necessary. You can do anything in this class with just a plain old scientific calculator if you wanted to, right? But TI-83 and TI-84 they'll do everything much faster. Okay. All right. So we did convert to radians. Now let's convert to degrees. Okay. So here's my example here. For part A, let's say we have pi over 3 rads. Okay. For part B, let's say we have negative 5 pi over 3 rads. And then for part C, right? Well, let's do 1 rad. Yeah. Okay. All right. So for part A, yeah, negative 5 pi over 3 rads there. Yeah. All right. So pi over 3 rads, right? So we're going to be multiplying by 1 in a funny way. Okay. Times 1, right? So this is pi over 3 rads times. You can look above where I have the formula up there. But remember, we just want to cross off radians, right? So we're going to divide by pi rads in order to do that, right? And so we have to say that pi rads is the same thing as 180 degrees. So we're multiplying by 180 degrees. We're dividing by pi rads because we want to cancel off the radians, okay? So my rads will cancel off. My pi's will also cancel off. Now, pi divided by pi is 1, right? Not 0. A lot of times people will see pi upstairs, pi downstairs. They'll cancel them off and they'll just get to 0. That doesn't happen. Yeah, okay. Yeah, you're dividing there. So pi over pi is 1. So this would just be 1 times 180 divided by 3, which is 60 degrees. Okay. All right. Now let's do negative 5 pi over 3. Same process, right? Exact same process. Multiplying by 1 in a very funny way. Again, we get some cancellation. My pi's cancel off also, right? We already know that 180 over 3 is 60. So then negative 5 times 60 is negative 300. Okay. Fair enough. And again, you can plug that into a calculator. All right. Now the last one there. And this is where a lot of people tend to make some pretty critical errors. Now clearly there's no pi in that, right? It's just 1 rad, right? Fair enough. Just 1 rad, right? There's no pi in there. Okay. But a lot of times people will insert pi in there because they think there's supposed to be a pi whenever you're talking about radians. It's not true. Pi is just a number, right? It's just some numbers, 3.14 and so on and so forth. You can have any number of radians you want, including a whole number like 1. Okay. Fair enough. So don't put pi's in where there's not supposed to be pi's, right? 1 radian. And we're going to multiply it by 1 in a funny way. So we have 1 rad times 180 degrees divided by pi rads. Okay. So my rads cancel off. Okay. And I just have 1 times 180 degrees over pi. So that's 180 over pi degrees. Okay. And that's an exact answer, right? Now, people will see that there's a pi in there, and they'll be like, oh, doesn't that mean it's in radians? No, pi is just a number, right? It doesn't have units on its own, right? Yeah, it's just 180 divided by pi is some number, and you can plug it into a calculator. You can get an approximation, which I intend to do now. 180 divided by pi is 57 let's say 30. So this is approximately 57.30 degrees. Okay. Now, on MyLab Math, a lot of these problems will ask you for an exact answer. Okay. This is the exact answer. That's what you should put in for your exact answer. After you put that in as your exact answer, you click OK, and it'll say, yeah, you got it right, correct, and you'll get a green arrow. Then it'll go on to the next part of the problem. The next part of the problem says, now round at the 2 decimal places, right? And then you would put this in for that field, and then you'd get that one right as well, okay? So you need both the exact answer and the approximation, usually, is what they'll ask for, okay?